Thank you very much for the possibility to come here to this lovely place and also to present a talk to you. So I will be talking about a project that has been reasonably long already in the works. This is work together with my former honor student, then PhD student, Chris Stevens, who is now a senior lecturer at the University of Canterbury. So the project I'll be talking about is the nonlinear perturbation of a black hole by gravitational waves. And I'll explain in more detail what this means. But essentially what we are doing is we are shooting gravitational waves onto a initially static black hole, and we look at what happens. Okay, so the no, it shifts left and right. So the motivation for all of this is the problem that when you look at gravitational radiation in the theory of gravitation general relativity, you find that
just playing to get something.
You find that gravitational waves are defined uniquely only or unambiguously only when you go to infinity. And only when you go to infinity, you have the notions that you normally have of radiation problems. You know what the radiation flux is, you know what energy momentum means. In GR, there are these guys that I'll talk about a little bit, the Newman-Penrose constants. And only at infinity, because the waveform or the gravitational waves are well defined, you can have the compute the exact waveforms. Otherwise, there's always gauge issues involved in this, and those go away only when you are at infinity. So the main motivation here is to look at the asymptotic information, because then we also get global properties of spacetimes, which is computing the total energy inside the spacetime. Look at the mass loss and all these things. The last issue that has to do with asymptotic structure is scattering problems, where you're thinking of some radiation coming from far away onto a system, interacting with a system, and then radiation going out again to infinity. And so you want to have a setup that allows you to describe things that come in from the infinite past and go out to the infinite future. And that's the setup that I will be presenting here. And that's ideal. Well, it is useful for scattering problems. Ideal, I'm not sure. But that's a different thing. So in order to reach infinity, what you do in GR is that you have a space-time that is a set of events described by time and space coordinates. And in order to get some sort of an evolution, you have to introduce time slices that tell you what time it is. And those have to be chosen. If you want to get this asymptotic information, you have to choose these time slices in such a way that they intersect null infinity. So these are called hyperboloidal hypersurfaces if they are space-like. And in that context, you will be solving a Cauchy problem. Or you look at null hypersurfaces, which also have the property that they intersect null infinity. But they are null hypersurfaces. And that means that when you use those slicings, you're solving a characteristic initial value problem. And those are principally different problems. And so it's selecting these things, these slicings, makes a big difference in how you can continue. Okay, so what I call Einstein evolution, this is where you foliate your spacetime with hyperboloidal hypersurfaces, and then I mean, you have the experts here, like Alex and Edgar and so on. And then you spatially compactify these hyperboloidal hypersurfaces. You still use the standard Einstein equations to evolve, and that means that you are, if you're looking at the vacuum situation, you have the Einstein tensor of that metric that you're solving for, which I call the G twiddle here. So you have the equations which are physical or Einstein tensor equals 0, and that will give you, under certain conditions, a metric that describes the physics. There is the a C here is missing, but this is CCM, that's Cauchy characteristic matching. This is where you try to combine the two different choices of slicing, where you have the space-like hypersurfaces that give you the Cauchy problem, and then you have a null slicings, that's things that go like a null cone that give you the characteristic evolution. And so there is a project underway also for a long time that tries to combine these two approaches in the Cauchy characteristic matching. And there is, you have to do some or a lot of work in order to combine those two completely different approaches by matching along a time-like interface. I'm not going to go into details here because that's not what I'm doing. The third approach, that is what I'm talking about. That's what I call the conformal Einstein evolution. This is where you use let's call it a trick that Penrose invented in 1962, I believe, where you have the metric that describes you the physics, and then you rescale that metric to get a different metric, which has the property that this metric allows you to attach boundary points to your manifold, and those boundary points have the interpretation as being at infinity for the physical metric. So this boundary that I denote here by this script I, which is usually just called scry. So that denotes the boundary points of the manifold on which the unphysical metric here lives. And the points of scry are ideal endpoints of light rays that go out the physical spacetime. Okay, so you can think of these, you're following the light rays until you cannot follow any further, and that's the ideal endpoint, and that's the point on scry. And so then we have this manifold with a boundary, and for that manifold we do the slicing with space-like hypersurfaces. So we foliate the conformal spacetime by space-like hypersurfaces. Those become automatically hyperboloidal when they intersect the boundary, and the task is then a little bit more complicated than before in the Einstein evolution, where we had an equation directly for the physical metric. In this case, we get equations for this pair, G and omega. So we get equations for those two quantities such that this combination of the two quantities is a vacuum metric and describes the physics. Okay. So the representation of the physical metric is changed into this pair, and you can see by this equation here that when you multiply G with factor theta squared and omega with a factor theta, then you get the same physical metric. So there is some sort of conformal gauge freedom, as this is called, in this representation. So the if you were going to take the Einstein tensor for this metric, or take the equations that determine the Einstein tensor for this metric, plugging in this expression here, you find that you will get equations or an expression that has powers of omega in the denominator. And the scry here, infinity, is where omega vanishes. You can see this here because scry, the boundary here is supposed to be at a finite place. So that means that the G is finite. The G twiddle is infinite because this is supposed to be infinity for G twiddle. So G becomes infinite. That means omega has to go to 0. And so the infinity here is where omega vanishes. And when you compute the Einstein tensor for the metric G twiddle using this representation, you find that that gives you equations that are singular because the omega appears in the denominator. And so you get a blow up of those terms wherever omega vanishes. But there are ways around this by reinterpreting these equations. And that is what's called the conformal field equations. And that's what I will talk about next. So I am not going to write many of these equations. This is just a qualitative description of those equations. In a sense, it's not really that much of a change from the usual Einstein equations, but it takes some thinking. So the origin of the conformal field equations is the Penrose trick, the conformal compactification. But when you do this geometric sort of transformation, there is not much information about how you should handle the equations, the PDEs that are coming from this. And this was developed, so the PDE aspect of this was developed by Helmut Friedrich in the 1980s. And he gave a system of equations which is equivalent to the standard Einstein equations wherever this conformal factor omega does not vanish. And the equations are regular at those places where omega vanishes. If there are any questions, don't hesitate to interrupt me. So these equations, they determine the space-time in a conformally covariant way. That's what I mentioned in the previous slides. It gives you equations for omega and the conformal metric, and there is this freedom in the by multiplying with a conformal factor. And so this is what is meant with conformally covariant way. Okay, so when you write down the standard Einstein equations, which is GAB is equal to 0, you express the GAB in terms of Christoffel symbols, and then GAB equals 0 is a set of differential equations for the Christoffel symbols. The Christoffel symbols themselves are written in terms of, depending on your approach, either in terms of first derivatives of the metric or in terms of derivatives of frame coefficients. And so you have a hierarchy of equations. You have equations for the frame coefficients, let's say, and then you have equations for the Christoffel symbols, and then you do something with the Christoffel symbols or the curvature expressions that are given in terms of the Christoffel. You have the same thing here. So we have equations for a frame, and the equation is essentially just saying that we want to use a torsion-free connection. That's exactly what the equations are saying in the standard Einstein setup also. Then we have equations for a connection, so that's equations for the Christoffel symbols. And that's just saying how you compute the curvature, the Riemann tensor, from the Christoffel symbols. That's the second set of equations. And then there is something new. In the standard Einstein equations, you would set the combination of those equations that describe the Einstein tensor equal to 0. So that would be the set of equations that you would solve. In this case, you get more equations. And this is because the unphysical Ricci tensor, so that's the Ricci tensor that corresponds to this unphysical metric, is not necessarily 0, like it would be in the standard approach. But it satisfies equations due to the Bianchi identity. So that's another set of equations that is in the system. And then in order to close the system, you need equations for the Weil tensor. in our case, it's the rescaled Weil tensor. So it's this object that I call K here. And the equations that you get come from the Bianchi identity and the fact that you want the physical Einstein equations to hold. So the physical Einstein tensor or Ritchie tensor vanishes. And that gives you a set of equations that looks like this, which is a well-known set of equations. Because if we were in Minkowski space, this would be the equation for a massless spin-2 field. So that would be something that describes a graviton, whatever a graviton is. But as you know, also in the standard case, we need gauge conditions. So we have to say what are our coordinates, what is the frame that we are choosing. In our case, we have to say what is the conformal factor that we are choosing. That is this conformal freedom that I was talking about. And there is an additional freedom that I have not talked about. This has to do with what kind of a connection do we want. That's something that I will not talk about unless someone asks me. Okay, so this means that what's below here is just saying that we need gauge conditions in addition to these equations. Okay, so the gauge condition that I'm using for this setup is what's called the conformal Gauss gauge, and this is a gauge that is of a geometric nature, if you want. So what one does is you fix an initial hypersurface, an initial data surface, like this thing here. Think of this as a three-dimensional surface where you have coordinates x, and every point on that initial hypersurface is fixed by giving a triple of these coordinates. And then we start what's called conformal geodesics. So that's a particular class of curves that are defined in this conformal setup. That's some uniquely defined curves, which are, what would correspond to geodesics in a metric, in a Riemannian space. So these conformal geodesics are curves that are singled out by a conformal structure and not by a metric structure. So we have these conformal geodesics, and we start them at every point of the initial surface in such a way that they go perpendicular away from that surface. And so we get this set of lines here. And then based on those lines, we can introduce coordinates by, these curves are parametrized. So there is a parameter along these curves. And we can use the connection that we have in order to say that if I have let me draw this picture here. If I have a frame down here, which is a triad, or I think that's what we call it, a Dreibein, at the initial surface, together with the perpendicular vector here, that gives you a tetrad. And then we require this tetrad to be parallel transported along these curves. That gives us a tetrad at all the points. Yeah.
So, question: how do you know that these curves will not intersect in general?
I don't. I hope.
Oh, okay.
I'll come to that.
Because this seems pretty similar to standard geodesic.
Exactly, and there they intersect. I'll come to that. Okay. And so we get a triad, a tetrad along the curves, and then we also get coordinates in a neighborhood of the initial surface by essentially just saying that we look at the surfaces where the parameter along the curves is constant. So this here is the surface where the parameter along the curves is equal to 1. There should be s equals 1 down there, and then the next one is s equals 2, and s equals 3 is no longer there. And then we can use this setup to fix all the freedoms, all the gauge freedoms that we have. So we have the frame. We can define, because these are special curves, we can define this so-called conformal connection. There is a unique conformal factor related to this, also coming from the properties of those curves. And so we have fixed with this choice, we have fixed all the freedom that is in the system. And now to your question. The physical geodesics, they tend to intersect because of the gravitational pull. I mean, this is what you just said. Time-like geodesics tend to, when you have the right energy conditions, they tend to come together and to intersect. So the physical Gauss gauge collapses very quickly. But in our case, where we are looking at perturbations of Schwarzschild, you can look at in exact Schwarzschild or in the exact Kruskal extension, what do these curves do? And you see that when you take a hypersurface like this, that goes through the crossover point here and then goes to space like infinity, you look at these conformal geodesics that come out perpendicularly from that surface, and you find that they do not intersect. They go uniquely all the way up to the singularity here, or up to scrum. And so the hope is that when you perturb the Schwarzschild thing, and you do not perturb it too quickly, or with a too big a perturbation, then this behavior is still true. Okay, so that's the hope, and so far this has been. So these curves, as I said, they cover the entire Kruskal extension, and we assume that the same holds for the perturbations that we are looking at. Okay, why using this gauge? Now, this is because the equations simplify tremendously when you use this gauge. So I've shown you a description, a qualitative summary of the equations. When you look at them in the gauge that I have described, you find that you can split the unknowns, the unknown field variables, into two cases, two classes. One I call U, and the other one I call K. I call them K because these are exactly the components of this K field that satisfies the spin 2 equation. All the equations, all the unknowns that are not K satisfy a system of equations like this. So this is an ODE, a nonlinear ODE, where K is essentially a factor, a parameter. And the K's themselves satisfy a partial differential equation. So you see the partial spatial derivatives here of the K's with coefficients that depend on U. And K also appears linearly. So this is a semi-linear equation for K, where the coefficients depend on the other quantities U. So in a sense, this is saying that K describes a wave phenomenon because the system here is easily shown to be a symmetric hyperbolic system. So it describes a wave propagation phenomenon. So you see that it's a wave phenomenon propagating on a background that is given by all the other quantities, where the other quantities are influenced back from the K. Okay, so in a sense, you can think of this as being some background that is established by the U's, and on that background, you have the K's propagating. And just looking at this system, this being an ODE, this being symmetric hyperbolic, you just know that this is a well-posed Cauchy problem. Okay, because symmetric hyperbolic systems is well-posed Cauchy problem. Okay, a little bit about the code, but I don't want to spend too much time on this. So we assume that we have time slices, t equals constant, which can be foliated by spheres. So we have onion-like shape in this time slices. And so we get one parameter that describes the radius, if you want, of the spheres. And then the angles on the spheres are the other variables. And so we treat the radial direction differently from the angles in the sense that we have a hybrid spectral finite difference code. On the spheres, we treat the angular derivatives using what's called the ETH calculus. Some of you will know what ETH is. It's a particular angular derivative operator on the sphere. And it's useful because in a particular basis, by spin-weighted spherical harmonics, this derivative operator is diagonal. And so you can apply a spectral method by doing transformations between the basis of spin-weighted spherical harmonics and the space representation. Yeah. I think that's just another name.
Oh, okay.
I think spin-weighted is always refers to what I call spherical harmonics.
So the spherical harmonics when like the spherical harmonics?
But I think the spherical harmonics just have an extra parameter which relates to wavelengthness of the function of the receiver. So it's very similar, but they have an extra parameter which tells that they're wavelength rather than being spherical in a way.
Okay.
But the algorithm is similar.
Yeah. I mean, in my book, there are only spin-weighted spherical harmonics, but it could be that these are some specific linear combinations or something. Right. So that's what we do on the sphere. And in the radial direction, we use fourth order finite difference using what's called these summation by parts operators that come from looking at discrete energies and trying to preserve the energies in the evolution. And so, because this here is very general, this is full 3D. By restricting the representation of the in terms of spherical harmonics to only be, you have these angular quantum numbers. I think they are called L and M. When you have only functions that have m equals 0, you're describing an axisymmetric situation. And so if we restrict ourselves to m equals 0, then we do calculations in axisymmetry. If we allow arbitrary m's between minus L and L, then we get the general 3D case. Okay. Right, then you have to look at the usual problems in numerics. That the code that we have written is what's it called? Free evolution, which means that we have to look at the constraints and see whether they are satisfied. So we monitor them continuously, and in all the cases that I'm presenting, they are satisfied to a sufficient level. We also have to talk about boundary conditions. This comes down to looking at these SBP operators, and there is a particular class of boundary conditions which called maximally dissipative. Again, this comes from looking at energy methods for the numerics. And so when you look at the evolution system for the K, and now I'm switching from K to psi, this is the same thing. So these are complex components of the K. This is simply because these are more known in some circles. And it's easier to write down equations for the complex combinations. So when you look at the evolution system, you see that there are two modes that meet boundary conditions, the psi0 and the psi1. Psi0 is an S equals 2, spin weight 2 function. This is a spin weight 1 function. On physical grounds, you expect that there is only one degree of freedom that is allowed to come in, that is an S equals 2, so one gravitational wave degree of freedom and nothing else. So in order to get rid of the psi1, you need to look at the constraint propagation, so what the constraints are doing. And for the constraints, you can derive a system of equations. And so if you insist that there are no what's called constraint violating modes coming in, that gives you a condition that the psi1 has to satisfy given the psi0. So once we insist that there are no constraint propagating constraint violating modes coming in from the boundary, we have one physical degree of freedom per boundary. And that is the degree of freedom that you would expect, namely it's a free gravitational wave degree of freedom. Okay, so now here is a picture of the situation that we are looking at. So we look at a static black hole. So essentially from this picture, which is the full Kruskal picture, we take this initial surface here. On that initial surface, we have the exact solution of the exact Schwarzschild solution. Then we set up an inner boundary and an outer boundary. And the inner boundary is chosen such that it's in the trapped region so that everything is going out of the computational domain. So we do not need a specific boundary condition here. We just impose the equation at the boundary. At the outer boundary, we have this, we have to specify the gravitational wave that is coming in. And so that is done at some part of the boundary, which is given here in blue. So there is a finite train of gravitational waves coming in. And then we go back to zero. Then the property of the gauge is such that we start at a finite, at a sphere with a finite radius, and then the gauge carries us through null infinity here. And so that after that point here, we have points of null infinity, so of the at infinity for the physical spacetime in our grid, and we can look at what's happening at these points. We can also study what's happening close to the singularity, well, to a certain extent, and in particular, what is happening in this region where the horizon is coming together with the singularity and null infinity. So this here is a really interesting spot, and it's very complicated to look at. So keep this point here in mind, because in the next, maybe the next of the slide after the next, I'll show you the actual picture. Okay. Yes. So so this is the numerical, the computational setup, and so we take the initial Schwarzschild black hole, which is always the same. For some reason, we choose m equals 1/2. Ask Chris about that. And then we vary the information of gravitational waves that is coming in. Okay. And so what I usually say is that we have this black hole, which you can think of as sphere, and then we grab it with gravitational waves. And if the straightforward thing is to have gravitational waves coming in from all sides, and then what we do is we just shake the black hole. So we shake it. And what I also want to do, which we have started to do, is not shake it, but kick it. Kick the black hole, where we have gravitational waves coming in from one direction mostly, and then see what happens to the black hole in the evolution. What do we see at infinity? And the next thing, which is even more complicated, I think, is that we could also probably spin it. So by having gravitational waves that carry angular momentum into the system, we could make the Schwarzschild black hole spin up into a Kerr black hole. And well, into something like a Kerr black hole, which would then settle down to an actual Kerr black hole. But we have not done that at all. Okay, so as I said, so far we can shake the black hole, and that means that we do a perturbation on it, a nonlinear perturbation, because our gravitational wave can be quite strong. And so what we are doing is a nonlinear perturbation. We look at the transient evolution with a large wave amplitude A, and we do our computations in the time domain. People here might be more familiar with the linear perturbation of the black holes, which usually is done, well, it is done with an infinitesimally small amplitude, obviously, because it's a linear perturbation. You see these particular modes, these quasi-normal modes called the ringing, and the computations are done in the frequency domain. Contrast 2 hours in the time domain. But I know that there are computations also done in the time domain. So when you want to make a comparison between a nonlinear perturbation and the linear perturbation, you have to think about things, and that took us quite some time. Okay, so this is the picture that I wanted to show. This is the output of that idealized picture here that I mentioned. So here I'm looking at, well, it really is this entire area here. But you see here that, so this is what's called, the title is down there. So this is psi 0. That's the component that needs a boundary condition here. So here is the incoming radiation, and it goes through the space-time. It goes through the horizon, and then it vanishes near the singularity. So I should say a little bit about these various features here. So the green line, this is an approximation to the horizon in the sense that every point on this green line is the largest sphere on our grid that is entirely trapped. The next sphere, which is a little bit larger, has regions where it's untrapped. So this gives us an approximation of the horizon. This pinkish line here, this is null infinity. These steps here come because we are cutting off the grid every so often along the evolution, and then we regrid in order to keep the same number of points at every step. Same thing happens here, close to the singularity. When the curvature becomes too large, we cut it off and throw it away, and keep only the points that are further away from the singularity. And so what you see here is that you have this strong signal coming in, and then you see these features here, this yellowish bulbs here. You also see, when you look closely, that close to the incoming radiation, you see another yellowish area here. Then it's dark again, then it's again yellow, it becomes dark again, yellow, and there is, when you zoom in, you see another bulb up there. And so what you see here is that the space-time that is, in to the future of the ingoing radiation somehow is excited into various, I wouldn't say periodic, but into various stages of excitement. And those things are exactly the precursors of the ringing. So that's the transient behavior that you see that will settle down into the ringing when you follow this for longer times, which we cannot do because of the gauge that we are using. So this here is a zoom in, where you see these bulbs here again, and here is this the next bulb that I was talking about. Again, I should say that this is a cut through the equatorial plane that shows that gives you this. It depends on, because it's an axisymmetric computation, this depends on the angle, but it's qualitatively always the same. And so what you see here is that there is the ringing, which is a global phenomenon of the entire space-time. It's probably more visible on this one. I have an even better picture later on. But you see that the incoming radiation gives you these areas where the space-time is in excitement. Okay. So then I told you that we can look at null infinity, and we can look at the Bondi mass. So this here is the behavior of the Bondi mass for an initial mass of m equals 1/2. And this at roughly 0.8 something, we see the the intersection of the hypersurface with null infinity, and that's the first time where we can compute the Bondi mass. And you see, with depending on the amplitude, here we get somewhat different behaviors. First of all, the first value of the Bondi mass at here, and then for the green and the red one further up here. This scales with the amplitude squared, but not quite, because it would scale exactly with a squared if this was linear. But this is nonlinear, and so it scales a little bit less than a squared. But you also see the ringing, the sort of ringing here in these step-like behavior. And then we know from the analysis that there is the massless formula, which says that when you look at the Bondi masses at two different times, then the difference between the masses is equal to the gravitational energy that has left the system between these two instances. So it's this formula. And because we have all the quantities that we need in order to compute the Bondi mass and the Bondi news, this n here, and the geometric things that make up the volume element here, we can compute every quantity in here, and we can look at the residual of this quantity and check how well the massless formula is satisfied. And when you do this, which was quite an effort to actually get all these expressions here. When you do this, you get this picture, which says that. So what you see here is this this thick strip here. This is a line that goes up and down, so it oscillates because from one instant to the next time step and so on, there is numerical error. But overall, you see that we get quite a constant behavior here, where the residual is roughly 2 times 10 to the minus 9. And that is to be compared with the initial mass of being of order 1, namely 0.5. So we see that when we are coming close to that point, which is time like infinity, there we get some larger deviations. But up to there, this is quite nicely satisfied. So once I saw that picture, I was pretty convinced that the code is doing things correctly.
So how do you compute the Bondi mass?
Well, there is a formula for the Bondi mass, which is psi2 minus sigma times n. But you have to interpret those correctly, because this formula is only in a particular gauge. And because we do not have that gauge, we have to do things in a more general way. So it is complicated to compute this thing. But I can show you how to do it. Okay, so this is a very similar picture to what I showed before, except now this is a, previously it was a psi0 with L equals 2, so a quadrupole. This here is an L equals 4, which is what? A quad 8, whatever. So L equals 4 mode. And for those of you who know the quasi-normal modes, you know that the frequencies change with L, and the higher the L, the higher the frequency is. Which means that we see in the same sort of time frame, we see more bulbs. It happens more quickly. And so what we wanted to do was look at these pictures here and compare with the quasi-normal modes. And so what we do in order to make a comparison, this is still not ideal, but that's the only thing that I could come up with. You introduce observers, that's these lines here, which have the property that they have fixed spatial coordinates. So the angular coordinates are the same, and the physical radius of the sphere that they are located are always constant. So that gives you these lines. In Schwarzschild, those would be static observers. Here they are not, but we call them quasi-static observers, just given by fixed spatial coordinates. But we take those, we compute the physical proper time along those curves. We compute the physical proper time in the Schwarzschild case, and we refer the frequency to those times. And then we can compare. So when we do this, this is what I just said, essentially. So we look at quasi-static observer, and we refer to the physical proper time here in order to make a comparison between the time difference between these bulbs here and the ring. And so what we do is we take along one of these observers, we take the signal that does something like this. We compare, or we compute the time between the maxima and minima of the signal, and that gives us half periods, essentially. And then, depending on how long we take this, what we should see is that this should approach the quasi-normal frequencies. So when we make a list, and I'll show you both, if we look at the ingoing mode as an L = 2 mode, then the linear frequency is this. And so when we compare this E1, E2, and E3 refers to the particular half period that we are looking at. And we look at the difference between the linear frequency and the time that would correspond, given that frequency, the time that would correspond to half a period. We can look at the difference. And you see here that when we look at the L = 2 mode, that's the one that was going in. You see that the differences between the half periods goes down. Similarly here for the psi4, that's the outgoing gravitational wave that also goes down. Whereas the L = 4 mode, that is the one that is created because of the nonlinearity that would have this frequency here. If it was a pure linear L = 4. But you see that that does not approach anything, that this is foreign to the linear frequency. So this L = 4 mode, this non-linearly generated mode, has nothing to do with the ingoing L = 2 mode. And the same thing goes here. Well, sorry?
What are they mean? E1,
E2, E3 is essentially these between this and this, or this and this. The times between maximum and minimum.
Sorry, can I ask on this plot? So why is it going up, the oscillation? Because I mean, we are used to think quasi-normal mode as damped oscillation. So why?
Because this is still the transient behavior.
Okay, so if you wait long enough, then you
see here that it goes down. Then, but yeah, we cannot follow this for a long time, so we do not see the exponential decay.
Okay.
We can see the frequency that however you call it, the real part and not the imaginary part, or the other way around.
Yeah, but so you're sure it's quasi-normal mode then? Because I mean, at early times you have a lot of different contributions also.
Why are we sure? Because it roughly corresponds to the frequencies.
Okay.
And so when we do this with an L = 4 mode, you see that the L = 4 converges to the required linear frequency, but the L = 2 does not. And the L = 2 is also generated by nonlinear interaction between L = 4, between the nonlinear. Okay. Something about the these are particular combinations or integrals of particular combinations of these psi quantities over a cutoff scri. And the equations that these psi satisfy on scri say that these things are constant. So there is no balance law like there is for the mass quantities. It just means that wherever you compute those things, you get the same value. Okay, so these are constant. They are constant because you can in some way represent them as the value of the rescaled Y tensor at a point. This point is I0, I plus, which usually is singular, so that's why it's a virtual value. But in situation where the I plus is not singular, you get exactly the value of this thing at that point. That's why it's a constant. And so there are 5 constants corresponding to I equals 0, 1, 2, 3, 4, or corresponding to m equals -2, -1, 0, 1, and 2. In axisymmetry, obviously, because m is restricted to 0, there is only one quantity. So what we did is we looked at these expressions and tried to see whether they are constant. And within numerical accuracy, they seem to be constant. So this here is the time over which we were following them. And this is the value given the particular resolution. So if we increase the resolution, these the log 10 error of non-constancy, so this is the difference to the first value that we encounter, this goes down. And so that means that numerically, this seems to say that they are constant within numerical accuracy. So if we would increase the resolution even more, we could make this even more constant. Essentially, it's the same. So that means that these quantities that analytically should be constant, numerically look to be constant. Now there is some conundrum with this that comes from the analysis again, because generically this null infinity is not smooth. You can have polylogarithmic terms. And when you have those, the Newman Penrose constants are not constants, they depend on time. And now we see that numerically they seem to be constant, but you could say that numerics, usually introduces errors. And so you could think of those errors being generating polylogarithmic terms. And then that would mean that the Penrose constant would not be constant. So that's a sort of a conundrum that I do not know how to resolve. Here are some reconciliations, but I do not know what is true. And it's some questions that one can look at analytically and numerically if one wanted to. So what we see is that numerically they seem to be constant. Analytically, one should give an argument why they should be constant. Okay, now I want to talk a little bit about the, I should come to an end, I guess. The kicking the black hole. So this is something that we have just started to do. So what we want to do is what I said earlier is we want to take the black hole. We shoot gravitational waves from one direction because we do this in axisymmetry, it's the positive z direction. And then we want to measure what does the Bondi momentum tell us about the this process. So this is the signal that we see. So this is the Bondi moment, the linear momentum in the z direction as a function of time. And that's all I can say. So this is the curve. I cannot interpret this to you at the moment because I do not know what momentum we have shot in. We have put in a gravitational wave coming from the z direction, but because we are on a finite surface, I should compute what is the linear momentum on that surface corresponding to that wave. And there is not a unique formula for that. That would be a quasi-normal energy momentum formula, and those are not decided about definitely which one to use. So at the moment, we are looking at this definition by Dugan and Mason, which seems to be the one that has the most promising features, but we still have to compute what we are shooting. And so what this part of the project is about is to essentially compute the cross-section of the process of a gravitational wave scattering or influencing the black hole by looking at the impact parameters of the gravitational wave, looking at the frequency of the gravitational wave and the amplitude, and then somehow make some sort of a scattering matrix also that allows us to say something about what happens when that momentum comes in, what momentum is given to the black hole, and what momentum is coming out as gravitational wave again. So that's the goal. Okay, final topic is this one. Oops. Where we look at scattering, and that's a very recent thing that we just published. So the idea is the following: we want to have gravitational waves not coming from a finite surface, as we have done so far, but from infinity, which means that we need to be looking at what's called scry minus. That's the null infinity at the infinite past, and we specify data on that surface. We shoot that in. There is a there is a black hole inside here. So we shoot that in. There's an interaction between the black hole and the gravitational waves, and then gravitational waves come up. And in this way, we get a real scattering process between gravitational waves and the black hole. And so far, we have done this by cheating. Because we know how we do this with Schwarzschild. You see here this picture here. Initially, or previously, I had the initial surface at this level, where it goes through the crossover and spatial infinity. Now I take the surface to the past, such that it intersects null infinity here. And then at this boundary that is not visible here, at this boundary, I shoot in gravitational waves. This will come in, travel through the unphysical spacetime, and then enter the physical spacetime through null infinity at this location here. And then we do what we have done before. So in this way, we well, it doesn't show here, but there is I0, which is a very complicated spot, and by doing this, we avoid dealing with I0, and we just give data inside the away from I0. But yeah,
wouldn't the inner boundary be problematic in this case? Like, what kind of boundary conditions could we put in there?
Yeah, that's a good question. I was asked this before. What we do here is that it's purely outgoing radiation. That does not seem to be a problem.
Okay.
Okay, that's the only thing that I can tell you at the moment. Yeah, the only other possibility would be to make this exact Schwarzschild also, and I forgot what we are actually doing there. Yeah, but yes, that is an issue. But as I say, for the numerical evolution, everything is okay. So nothing happens there. Okay. So that's this picture. And so here, this diagram basically summarizes everything that is interesting to know. Let me go back to this thing. So what we do here is that we put in a gravitational wave pulse of finite time that is at the outer boundary here, and then it travels through the unphysical spacetime. While it travels through the unphysical spacetime, it creates backscattering, and the backscatter creates another second-order backscatter, and so on, which means that when the radiation reaches null infinity, it's no longer a finite duration pulse, but it has a tail. And when you look at the blue curve here, you see that this is the first pulse, and then this is logarithmic here, so this goes to 0 down there. And then you see that there is a tail that is created by the traveling through the unphysical spacetime. And that is what I mean with cheating. Ideally, you would like to give data directly on scry minus to avoid exactly that phenomenon. But we cannot do this because we are too stupid to compute the initial data on scry minus. So that's why we have this tail here. And then you see the red curve here is the Bondi energy, which, because we are on scry minus, continuously grows. And then n bar is the flux and so on, which is all, that. Okay. The only point that I want to make about this computation here is that we can compute the energy, the total energy that has entered the spacetime, and we can compute the total energy that has left the spacetime at scry plus, and we can look at how these, we can compare them. When you look at this as a function of the amplitude of the ingoing wave, you see that the most of the ingoing energy stays in the spacetime. It basically increases the Bondi mass, and only a little bit, when you have a weak wave, only a little bit comes out. When you increase the wave, like doubling the amplitude roughly, you see that this ratio here changes, not linearly, but more, and that means that the more you perturb the spacetime with the ingoing amplitude, so the more you bang on the spacetime, the more reaction you get, in the sense that the spacetime starts to vibrate, and this vibration you see is outgoing radiation. So when you have amplitude 10, then a fifth of the ingoing energy is outgoing, whereas before it was only 8.
So one question is, like, I know your discussion has been in charge of spacetime, but would you try to do this in Minkowski so that these numbers actually like close to 1 or something, like
What do you mean in Minkowski? I will.
So that none of the energy that you put into the spacetime is not captured by the black hole, but just scattered.
In principle, we should be able to do this. Numerically, it's an issue. This is because I told you we have this spheres, one inside the other. In Minkowski, you have a sphere that corresponds to r equals 0, which is that gives you a coordinate singularity, and that is something that we have problems with. Numerically, this just blows up, and I don't know what to do.
Like usually you would use a staggered grid, no? So that there's no sphere exactly at 0. Wouldn't that be enough?
Well, that's not how we do things, but it is something to explore. And that's, I mean, I'm open to all kinds of suggestions. That's
but sometimes then it's unstable, right? You need to modify them to get stable.
So here is the further research. I don't want to bother you with it. It's just some questions, or mostly questions, that I do not know the answer to. So I'll stop here. Thank you.
Any questions?
Yeah.
Yeah, go on.
Yeah.
I just didn't quite get what was the problem in giving the initial data at scry minus.
Yeah. Well, So that's, you need to compute the, you have to specify all your variables at square minus. Okay, there's one free quantity, which is psi 0. There is the psi's, they satisfy a hierarchy of ODEs along this. And I would guess that in this setup that we have, where you have, you know, only a piece of square minus, you could solve those equations. But if you wanted to do this on the entire length of square minus, you have to satisfy boundary conditions at the beginning and the end. And that gives you conditions on the psi 0, which is, I think, very non-local, and I have not figured out what these conditions are, so that, you know, all the psi's that you integrate up with and you get integration constants, all those psi's have to satisfy particular regularity conditions at I minus and I 0. And so it's a, you know, it's a problem where you have conditions at both ends and only an ODE in between. And so that's tricky.
I want to ask about IQO. So because you were saying that, so there are problems for longer time.
Yes.
So I understand from the point of view of conformal physics, I mean, they go all the way of I plus and they would be at a finite.
Analytically, it's not a problem. The problem is that when you want to follow the quasi-normal modes, then you want to do this in the physical time. And because of the conformal rescaling, the difference between physical and conformal time is just stretched out. Yep.
I wonder if you plan to go for this Scanlon problem, you actually assuming the value to the state. Wouldn't you have this problem of like you are interrupting the evolution at a finite time? For example, in the quasi-normal mode, but you're still some energy increase. So maybe you're just stopping before a lot of the energy has actually stayed.
Yeah, that could be. That could well be. You know, so it is something that I do not have under control, right? It's just what the code tells me at the moment. If we would extend this, then we might get different numbers. But
you don't know if, like, you don't have any way of quantifying how stabilized the bottom mass is.
Not at the moment, no.
Yeah, so about the frequencies.
Yeah.
So just to make sure the initial palettes that you said that it doesn't already have the possible mode.
No, this is basically, I think, in all the computations, we only have a bump like this. So it's only a half period.
Then naturally somehow.
So this problem of the conformal time and the physical time kind of deviating as you go towards I plus, would it be possible to make some choice of gauge that alleviates that problem?
It would be possible, but then you're losing the simplicity of the equations that I was showing.
So it wouldn't be symmetric hyperbolic, for example? Or
Sorry?
Would you lose symmetric hyperbolicity? Or
No. What you lose is the fact that most of the equations satisfy ODEs. You lose this part. This remains, but when you're lucky and you choose the correct gauge, then you can make some of those things also symmetric hyperbolic, but it means that you have a much bigger system to deal with and so on. So it's much more complicated to deal with. And so that's why we chose this gauge, because it allows you to do something in finite time. But I did not anticipate that, you know, the problem with the time stepping becomes such an issue. That's something that I have to say I'm quite disappointed with it, but that's what it is.
Yeah, a question for like say extension of the word. So the way you satisfy the constraints in the initial data, you just put pure Schwarzschild, right?
Yes. Yeah. So it automatically satisfied.
Yes, exactly. And like the question is like, say if you had matter, like could this procedure of the conformal geodesics be generalized to have matter in the initial data?
It depends on the matter. There are ways of dealing with it when your matter has an energy momentum tensor that is trace free. in general, things go bad and it doesn't work.
Okay, I see. Well, and related to that, probably doesn't matter. So the thing is that for the initial data that you take now, all the constraints are satisfied exactly, right? But if you have matter, even if some matter that goes well with the probability, in some cases you would need to solve it numerically, right? And then you would have violations, constraint violations, you know, the truncation error or something. But the CFEs, you know, have a lot of constraints. So the question is, like, is there a way to study if these constraints will grow, right? Because I mean, I know you mentioned that you monitor the constraints here and they are good, you know, during the evolution.
Yep.
But probably they are too well satisfied in the initial data, right? Like, is there a way to know what will happen with
I
the
do
constraint?
not know for this system, but in principle, I mean, the question is general. So I have many years ago, I have written a code for a different kind of the conformal field equations, which was did not use the conformal geodesics, and that was a different system where this part was, as I said before, was made up of subsystems that were symmetric hyperbolic. So I did the same thing. You solve the constraints initially to truncation error, as you say, and then you monitor and you observe that constraints are doing something. There is no complete analytic treatment of what the constraints are doing, but I did with a student of mine at the time. We looked at the constraints coming from this system, because that's the main part of the system, of the entire system, because that gives you the gravitational wave propagation. And there you find that the constraints, you do some sort of stability analysis for this system, and coefficients in here and here, mostly here, are the extrinsic curvature and the acceleration vector of your time foliation. And you find that, and I forget which it was, if the time slices are bent in this way, constraints go down. When they are bent in this way, they increase. So they diverge. So there is a definite influence of the time foliation on the behavior of constraints. I would have to go back to that paper to exactly tell you, but that was the main factor. It was the mean curvature of the time foliation as an influence on convergence or divergence of the constraints. And there is another criterion that has to do with, I think it was the size of the acceleration or something, that also influences this. But that's the only, the only systematic treatment of this sort of constraint violations that I know of, apart from these constraint damping terms that people are using.
But can you put constraint damping terms in the data?
Sorry? This,
can you put constraint
we haven't done that because the constraints are reasonably satisfied without them.
I was going to actually ask, so when we see scribe, it's like this first line, and you then take the
This one.
Yes, but so let's say the shape we can see of the bottom line, which I understand is scribe.
Yes.
That is basically determined by the conformal transfer.
Yes.
So are there, I am not familiar with the page, are there any parameters we can use so we can modify that profile?
Yes, so this, I told you that the conformal Gauss gauge, where's that picture? Essentially this one. We start them perpendicular to the initial surface, but there's a freedom, you can change the angle. But I think this is the only freedom that you have. When you do this, you change a little bit the shape of this here. And initially we were thinking that maybe by changing the angles, we could blow this up here, this region here in some way and get a little bit more time. But it helps a little bit, but not much. So there is a freedom to do things, but that's not really well explored.
The black hole.
Yeah.
Are you describing when you finish your?
This is the value of the essentially the square of the psi. You know, the one of the curvature invariants. And you say when this is higher than particular value, then you cut it off. That gives you this shape.
No further questions? Huh?
If you have seen anything happening around the light wave, because we are talking about conformal models,
yeah.
And it seems I'm a bit surprised, let's say, to see that the box goes in,
yeah,
and then only sometime afterwards you see something that seems like it's coming from inside the horizon. I would expect you to see some kind of build up of curvature around the light ring. And this
Where is the light ring? What do you mean with the light ring?
This is the part, but
yeah.
So this,
Oh, you mean 3M? Okay.
First for large L, so maybe for L equals 40,
yeah.
There's this connection between well, with this then equals 0. So I'm not sure if this still.
So I should say we have not looked particularly at R equals 3M. Could be that there is something happening. I would not know what should happen because we are not dealing with geodesics in that sense, right? Like you know, null geodesics, physical null geodesics. So I'm not sure, but I just don't know. I mean, what do you expect to see?
Because for large L, cardinal model that get trapped around the light ring.
Oh,
yeah,
I see.
they should be localized around that.
Yeah, I mean, what we have done is L equals 4 and I think L equals 6. So
It's already large enough.
you want to see something?
Yeah,
Yeah.
I think so. I mean, if you apply formula for large L to L equals 6, it works quite well for the frequency.
Okay. I mean, that's something that we could certainly look at. Yeah.
Yeah, I don't know.
Yeah, I have to say I do not know much about quasi-normal modes where they currently are. I mean, I know how to get them and so on, but current research I do not know. So you tell me.
I think maybe you're seeing some kind of buildup of curvature, and then these waves that are leaking out, they're leaking out of that region, and then eventually when it's settled down into a stable partial black hole, which is normal, I think.
Yeah.
All the energy will be going.
I mean, you know, as you can see, I mean, that's how far we can get, and that is, I think, 3 or 4 of these rings, and that's not much in time. So maybe all of this happens up there.
Yeah, I would think so. Yeah.
Like because imagine if you go further into it would be like seeing like some say yellow patches like this and some around
Yeah, I don't know.
That doesn't make a difference much. I mean, this all those functions, you know, for the quasi-normal modes, they all go more or less the same way. They have more or less the same behavior.
Yeah, but I think you should wait more because I mean, on the plot where we were seeing the oscillation, it's still growing at the end of the. I mean, we are not really in the quasi-normal mode region.
No, definitely not. That's,
you have to. I would think we would have to wait a bit more to see the decaying part.
Yeah, you see, that's why I'm saying I'm a bit disappointed with the time evolution here. But
if you enjoyed the video, like and subscribe.